Okay, welcome back. So let's just check we've got the right. Okay, we've got the right slides. Okay. Okay. Well, I've got a set of slides on reliability and validation, and after that I've got some case study. So we'll see how far we get today and then tomorrow. So you may have all seen this curve. We call it bathtub curve because it's the shape of a bathtub. And just to summarize, really we want this is failures. Really we want no failures, so it should be 0 down here, but in reality you don't get 0 failures in life. So we have the burn-in, or what we call the infant mortality region. We get high failure rate in most products. This is the only product, not just electronic, mechanical based things. So sometimes if it's a reliable product, this burn-in might be done in the factory. So the product's only released in this middle bit when there's a steady failure rate. It should be unusual that something fails. 1 in 100, 1 in a million, depending on the reliability. Then as things start to wear out, the curve starts to go up and it's end of useful life. It also applies to nature, unfortunately. Nobody yet lives forever. So you'll find this everywhere. So why is reliability important? Well, you need to think about what failure is, but we don't want any devices to fail. As I said, I think a couple of days ago, if you've got a mobile phone and you turn it on for any reason it doesn't work, you're not very happy. And if it's an emergency, a matter of life and death, that's very important. So some things are more important than others. Safety critical things like nuclear power stations, maybe some medical things, you have to be very reliable. But maybe mobile phones, not so. You think it's important, but in the great scheme of things, it's not so important. But they still are reliable. So lifetime will be product dependent. And for safety critical systems, if you want parts per million, you're talking about 99, and I think it's 49.999%. So to get the testing to do that is very difficult. So if you think of transistors now, we mentioned at the start that we can put about 10 billion transistors on a chip. So if one single transistor fails, that chip might not work. So it's like looking for a needle in a haystack. So you need to have the testing we talked about to be able to find that transistor. So finger products, we did talk about this before, just recently. How long do you think they should last? Well, mobile phone, I've had mine about 20 years, but most people change it every 2 or 3 years. But reliability is probably longer than that. But technology moves on, you want the latest products, the latest apps and so on, so you need to change it. Same with a PC. PC, 2 to 3 years, you can't run the latest operating system. It grows with the technology. When you're doing word processing, 20 years ago, a PC with a basic word processing package was good enough. But now people want to put fancy things even in word processing. And there's things there. You can think about, if you're designing about how reliable it might need to be. So theory of reliability there's a lot of theory though, it's still growing up. There's a lot of empirical formula, which means the sort of rules of thumb and fiddle factors, as I call them, built in. So these statistical empirical formula can predict or help predict how long a product might last, or you might validate it. But there's nothing better than testing it yourself to see actually how long will it last. So some companies will do burn-in on chips, and you might get a product in its middle stage of that bathtub curve. But if you want to do extended validation, it takes a long time. You don't want to wait 10 years to test a car. You want to do it in 6 weeks or 6 months. And it can cost a lot of money. So how do the electronics at any level, from chip level up to systems level, fail? Well, if you stress anything enough, electrically or mechanically, it will break. So the tester's job is to try and make it break and find out why. And the way it breaks, is that good enough so the product will last its lifetime or past its lifetime? So overheating is always a problem. Cooling in electronics, always a problem. Vibration we mentioned, so we do vibration tests, humidity. EMC effects, interference like these spikes this morning. It could interfere with your product or your circuit board or the product next to yours. And manufacturing faults, don't forget you're making electronics. Manufacturing faults at the chip level, of a circuit board level, or even when you put the thing inside a case. Any problems with that, you might have a problem. So when you get the failure in a circuit, a manufactured circuit board, the weakest link normally is the solder joint. Okay, and solder joint materials are changing. Used to have leaded solder. Lead came out of solder, or it's supposed to be out for most cases because it's dangerous to the environment. You have lead-free solder. Also in solder, we put in things like nanoparticles to change the way the solder behaves. And a lot of work in soldering technology and moving away from solder maybe to conducting glues. So literally glue the chip down on the board. Because then it's probably easy to recycle. So how do you check if a circuit works? Vibration might break the connections. Heating, cycling may break the connections. Moisture could cause short circuit. If you look at the chip, you imagine the biggest wafers are making now are about 300 millimeters or 30 centimeters diameter, quite big. Think how small the transistors are now, 10 nanometers. You get a lot of silicon die on that chip, all made in a production line. It's very difficult to make that chip. So you've got to test every single die on that chip. And the yield is essential. If the yield goes down to a low level, you can't make it, commercially. So I've listed the problems there. I won't go through them. So this is what I wanted. If you presented that as a electronics engineer and your boss said, how do you test that? Most of the things you want to look at are hidden. Okay? So inside there you've got multiple die. These are what we call stacked die. Could be memory. You've got chips there, and as I said earlier, the latest Intel chips, there'll be multiple die. You could have 4 die on that board, all connected together. Multiple in connections. You have what you call interposer boards, solder balls on the bottom and the top. One of those connections breaks. I think it's carry on. So what we do is we do validation testing. So to validate it in a reasonable time, we have to overstress. You want to test this? Okay, we'll just test the mic. What?
I just disturbed your
Yeah, because the mic's back. The mic went off. Yeah, it's sure. Yeah.
Actually, this course code I forgot to put.
Okay, that's fine.
That is why this is important.
Okay.
That is the reason why.
You got the pen on, yeah. No problem.
अमरेन जाओ चले जाओ बात हुई है बाहर आओ okay thank you.
Okay, hopefully the mic's back on. So we were talking about this over the last few days. It's not just classroom testing. We've now got a whole temperature range to go. If we're not 0 to 70, we normally will extend it. And I don't know if I mentioned it, but a colleague of mine in industry said to test a circuit board that's going into a car, an automobile, will cost you about £250,000. So to make sure that it's, that you're sure that it's going to work for 10 years. Once you've done that validation testing, not certain, but you're fairly sure it's going to work. But it's a lot of money, but if you're making 100,000 cars, it still adds price to the car, but then if it doesn't work, that car will be off the market. And the same for any product. So, there's another thing I just want to show you quickly, we're not dwelling on this. When you're looking at the soldering joints, we're getting very small. These are two slides from a colleague of mine in Hong Kong. And as solder joints get small, these effects, electromigration and thermal migration, where things gravitate away, are going to come in at the solder joint level and give you problems. So we've got a case study now on some of my research. Can we go to the next presentation? Next one? The next file? Okay, so what we're talking about next is some research we've been doing in Liverpool based on these things, on real products. This is it, good, thank you. So case study, we've got enough time, but I'll have to fly through it because it's got a lot of things. I'll concentrate on the key points, okay? You get copies of it so you can, if there's any problem you want to know, you can always email me when I get back, or you can discuss it tomorrow. I'll be here tomorrow. So, these are a team. It's always nice to work in a team. You can design on your own, but when you're doing things like validation and testing, you can share the workload. So, this is the team we had. And I'm an academic from the department. Dr. Guan Ming Zhang is an academic. I'm an expert more on electronic engineering. Guan Ming Zhang is more of an expert on ultrasound, which we use for the testing. He's a reader working with me. He's originally from China, although he had a short posting in Sweden before he came. He's been with me, working together since 2004. Ryan was a PhD student. He's from Malaysia. He did his degree and master's at John Moores University and his PhD, and then he got a job at Qualcomm. You may remember I said Qualcomm was just about to be taken over. I think it's something like a 260 billion takeover. Qualcomm's a massive company. So to get a job there, he's got skills in validation and test the industry wants. And then Derek, he was also a PhD student of ours, who works for this Delphi automotive electronics company. And he's now European validation manager. He manages test labs throughout all of Europe. So it's very key contact. So that's Delphi Electronics and Safety. That's Derek's company. We also are supported by Sonoscan, who make the acoustic microscope. And we were supported by Systegration, who do X-ray support. And Ryan was a PhD student. He's funded by, this is a government-funded research council project, paid his research grant. So just to quickly look at the key points. So we're looking at reliability of electronics in harsh environments. So in this case, it's automotive. Automotive is quite a harsh environment. Vibration, heating, cooling, water, anything can be coming up. So what's the environment? What's the point we're looking for in solder joints? What's the results we find? Can you use these techniques? And some quick conclusions. So there's Ryan. This is at Loughborough University where we gave a talk. Because Loughborough University is this centre, which ran for 5 years, which is now complete. This is a Ford Model T. We originally put it there. It's about 100 years old, and it's mainly mechanically based. Okay, but it was one of the first cars, well, probably the first car to be on the production line, and you could buy that, according to our information, with 4 months' wages at that time. So in America, you'd work for 4 months, you could buy a car. Not too bad. I don't know how that compares by today, but a lot of these cars were sold, and it's a famous car. Tin Lizzie, they call it. So here's my car, in my dreams. Now here's a car, came out in about 2000, absolutely stuffed with electronics. Everything's going to be driven by electronics, based on the Grand Prix cars, Formula 1 cars. So there's not many made, but as a test vehicle, it's really high tech. A test vehicle for electronics as well as for driving. Although it would be nice to have a test drive, but not on engine roads, on a racetrack. Here's my other car. BMW 7 Series is one of the top of the range BMWs. Very nice car. Price in UK about 50,000 to 150 now. We just brought out new models. But the key point is 100 microprocessors in there. 100. Might only be small ones, but it's going to be more. Even in small cars like small family car, there's hundreds of microprocessors going in. controlling everything. So anyone can go wrong. So it's a big problem. So when it comes down in price after 10 years, I might be able to get one second hand. Because this is a really nice car. I've been in one once. Driverless car. Okay, good idea. Well, driverless cars are also coming in. I think with the trials going on, Google car you've probably seen. But the idea is, all the autonomy is built into the car. It can self-steer, self-navigate, but it's still not there yet. How is it going to survive in India? I don't think it's going to be able to survive this junction between the campus and here on that railway line. I think there's been a couple of accidents here already, but I was reading something before I came away about the, how the sort of knowledge is embedded in there. There might be some problem with it. So I think it will come, but maybe in convoy on motorways. For general driving, I think it's still too dangerous. It's safer to drive a car here. I did offer to drive the director's car, but he said he didn't want to be killed. But I was willing to try. Not to kill him, not to try. Anyway, let's get back, because we've already got about half an hour, and I don't want to delay the next guy. So, again, 25% of the manufacturing cost, or the cost of a car, will be electronics. Bearing in mind it's a mechanical object. So you're in the right job, guys. 80% of innovation in cars is now in electronics. Active safety is what you're talking about, active safety for driverless cars. That's what Delphi call it. Active safety systems, the whole branch of technology being developed. All around the world, you want to get the first driverless car. Big business there. Electric cars are coming in. They started, they're a bit expensive, but eventually they will come in because of the pollution problems. In London, I think it's going to be electric cars, electric buses by 2020 to stop the pollution in London. So if all cities start doing this, your fully electric vehicles will come in. So the point is, it's hazardous operating environment. We're going to look at temperature, vibration, humidity, but high reliability is expected. So just a quick slide just to show you the sort of things you get inside a vehicle nowadays. This is quite an old slide. This is extended just to give you an idea. So you control the engine, electronic fuel injection, electronic timing, so on. Electronic ABS brakes have been there for a while. You've got active suspension, electronic suspension. Maybe you can tune it from sport mode on some high-end cars to comfort mode. So it's tunable. Four-wheel steering. Some cars available now park themselves. Have you seen these cars? I don't know how you find a parking space. If you can find a parking space, the car will reverse itself in. Because already they've got ultrasound sensors to gauge it. So, very high tech. And people want infotainment, it's called. Audio, video around the car. So if you've got children in the back, they can watch some video and be entertained. And you're on Bluetooth connectivity, so when you get in, your phone's immediately connected without doing anything. Excuse me. So just have a look at the temperatures there. These are typical temperatures in various parts of a vehicle. Now, oops. Sorry, let's go back. You see, if you put something on the engine, it's from minus 30, we have to assume it's for a cold country, up to plus 175. And we've worked on some products with Delphi with ceramic boards to control the engine, bolted onto the engine. And it was tried for 5 years or so, but ceramic boards are very expensive to make compared to the standard circuit board, so the cost drove it out of the market. But the production was quite nice. It's a very nifty board. And ceramic can take the heat. So better not to connect anything to the engine. Under hood, it's still going up to about 125, but you take it away from the engine, it's a bit cooler, so not as harsh. So it doesn't give you as many problems, and the engine will vibrate. If you can do it, engine controls maybe have to be under. You may be able to bring it inside the passenger bay, so it could be a bit cooler again, but still you've got quite large temperature range. I think the minimum one is minus 30 to plus 85. So when you're doing the testing, you have to do at least that, and if you want it to fail quicker, you have to overstress it. So in our test, we're going from minus 40 typically to about plus 130. So we've said this again, what's the lifetime? Is it 10 years? How long will the engine control unit or the ECU last? And we're looking at the solder joints because they are generally the weakest link. They will break first. So there's a typical chip soldered onto a board. As we firmly cycle it, the coefficients of thermal expansion of a board and a chip are different. We'd like them to be the same, then when it expands and contracts, will just stay nice, but they're not. And there's a big difference between a chip, silicon chip, and a circuit board, and the solder itself. So as it flexes up and down, you've got pressure on the joint, various things come into play, and eventually it's going to break. You're going to get some cracks. So that's what happens. This is a section joint, so you see the crack under the joint there now. So it separates. Once it's separated, mechanically it's not stable, so the chip will fall off the board if all the joints break. But once one separates, you've got an open circuit, it's in the bin or recycle time. So it's a coefficient of thermal expansion mismatch, and this cyclic fatigue are unavoidable. And what we did in our work is we took a product through a life cycle, trying to see exactly when it might break. So how did we do it? Well, you can't just cycle it for, say, 4 hours and cut it in half. Have a look at those solder joints which were sectioned, because then you've destroyed the product. We want to test it for, say, 6 weeks. So you need non-destructive testing, that's the key. Non-destructive testing means you can look at it, and we take it out of the test arena to do that. We look at it and put it back in. We don't break it. So we can use X-ray for that, although some X-rays can damage it if it's too high power, and you can use ultrasound because they penetrate through. Optical, maybe on the edges, but optical can't see inside a ball grid array, inside the solder. And a lot of ball grid arrays are underfilled with the component to make it more stable. So you can't put a fibre optic in there because there's no access. So you've got electronic probe on electronics. If you want to look at the physical cracks, you need some other method. We didn't have it available, but we have tried it at another university. 3D X-ray, like X-ray tomography, is coming in, but it's very expensive. That is another method. So just to reiterate there, AMI is like acoustic microimaging. We call it ultrasound inspection. And we're using that with X-ray inspection, join the two together in some data fusion, and we get the best of both worlds. So just a quick one. This is from a manufacturer data sheet, just so you know how ultrasound works. You have a pulsar there, sending ultrasound down. In our system, it's from about 5 or 10 megahertz up to 400 megahertz. So we need water to couple it. So when we're doing the sensing, the circuit's not live, but it doesn't need to be. So it penetrates through the water, and every time it says a acoustic difference between water and the chip, you get a reflection which we pick up in the same sensor. So we call it the main bang there, the first surface, the second, the third, you go down, but after a while it won't penetrate any deeper. Once you go through the circuit board, a circuit board tends to disperse all the ultrasound because of the way it's woven, because a circuit board is like woven with some fibre optics and some resin. It's not very good for passing ultrasound. So what we're interested in really is the top and the bottom of a solder joint, which it tends to break. In fact, it tends to break where it's attached to the circuit board here. We call this underbump metallization. We don't just, in the manufacturing process, solder it onto copper anymore. We have 2 or 3 or 4 layers of different materials to join the solder joint onto the copper. And this is changing as well. So this is how we do it. So this is a single point. It's called an A scan, going down. And what you do, you raster scan the A scan across your product and build up a 2D image. And you set a gate. So say you want to look at this interface, you set a gate just to consider this pulse coming off. So key is non-destructive test, not breaking the product. So ultrasound imaging is a little bit noisy. That's the trouble with it. So there's 2 pictures. This is part of our chip. It's got 109 balls. Ball size is about 140 microns. It's mainly 2 layers, and there's like 3 balls in opposite centre a bit. So these are when we're in good condition. You can see some reflection where the solder joint's coupled to the board because it's flat. But when it breaks and opens up, you get a bigger gap, so the intensity coming back, a bigger reflection goes up. So, and if you zoom in, that's a good solder joint and this is a broken one. So you have to work out how do you detect the difference. That was part of the problem. And we're still working on it. So that first one's good, you know, with a nice donut-shaped image there and quite a nice donut there. But when you get towards the edge, you get effects there. It's more difficult. It's not circular to see what's going on. And the last one, when you're on the edge of a chip there, you get edge effects due to the ultrasound moving around the board, and it's quite noisy. It's quite difficult to process. Okay, so one thing we did, you can see a difference in intensity. You can plot a histogram between a good joint and a bad joint. So obviously the intensity is going to get higher because it's reflecting more ultrasound, and we can try and detect when it's failed. One problem we found, this is why you do research. It's nice to find problems no one's found before. Normally the crack goes straight across. It goes in the same, more or less the same place, just underneath. It doesn't go in the flat area, it goes underneath this because you get what we call an intermetallic layer here. And this intermetallic layer comes down, it tends to break on the junction of the intermetallic layer with the rest of the solder. So normally it just goes down and so it goes across. But you can see this hole here, like a football. It's only 2D, that's like a football. So we call this a void. And during X-ray you can see it there. And again, X-rays are noisy, but you can see the detail. So a void is formed when you heat the solder up. We've got flux to make it, as you solder, to make it run. So I think the flux will boil. So it's like boiling some milk and there's bubbles coming up. And most of the bubbles will come to the surface and pop out. But some, especially if they're in the middle, because that's a spherical system, we only see the 2D, get stuck in. And we don't want voids. We want to avoid them. But that's the big one, but you could get several smaller ones. You might get 5 or 6 voids. So we need to try and, 1 or 2 is okay, because if you get too many, do you know what an aero bar is? You get aero chocolate bars here. You get like an aero chocolate where you smash it. If you've got too many bubbles, it's got to have a weak point and it'll break more easily. 1 or 2, maybe okay. So we'll go into this in a bit more detail, because what this does when we do the scanning, that joint is broken, but because you got this shape in the middle, because of the nature of it, it doesn't reflect the ultrasound as much. So this joint actually looks like a good joint. You can see that it's broken, and the reason it is this bit disperses all the ultrasound. So we found a way to solve it. So this is just working out the voids compared to the diameter of the joint. Anyway, we'll go back to that. So we're looking at the percentage voiding. So we came up with a figure for percentage voiding. As you'll see later, if it's more than a 3% voiding, which is what that bubble was, it affects the ultrasound image. So there's a blow-up X-ray, so that's the typical soil, that's with a void in, that's what it should look like without a void. The resolution on there is about 1 micron, and those balls across are about 120 microns, just so you have an idea. So there's our circuit board, back to the electronics. These are the flip chips, these shiny things, 8 on one side and 6 on the other, so it's a dual populated board, designed by the students, made in industry, so it's a commercial board. We had different types of solder, different types of underbump metallization, different types of surface finish. We've got a number of different flavors, so we can do different tests. So this is what a normal circuit board is called, FR4, have you heard of that? Stands for flame retardant 4. This is like the cheap circuit board, but it's used everywhere. And we used a 0.8mm thickness, which is quite important. 14 flip chips are placed on both sides. The flip chip's quite small. If you look at the end of your little finger, it's a bit like your nail. It's about just less than a centimetre by just less than half a centimetre. So quite difficult to handle. The thickness is 725 microns. It's got, say, 109 solder bumps. 140 micron height, but when they're being soldered it might just reduce down a bit. So this is our experimental profile. I need to speed up. So we decided minus 40 to plus 32. So for half an hour, this is in a chamber, we start from room temperature, take it up to 132 quickly as we can, hold it there for 30 minutes, and ramp it down very quickly to minus 40. So we don't have this facility in the university, so all our testing was done in industry, which is quite fortunate because talking about this equipment tonight, it's quite expensive equipment. So we set this profile quite aggressively, so the joint would break. We anticipated it would break in 100 cycles like this. One cycle effectively is 30 minutes at 120, 30 minutes at minus 40, that's one cycle. So it failed at 100 cycles. By medium fail, I mean all the chips fell off the board. All the solder joints have failed. So when you failed at 100 cycles, that's good. Not good for your product. But we didn't put this underfill in, so we deliberately designed the test to overstress it. So then we decide, okay, we're going to test it for 96 cycles. By that time, most of the chips will have fallen off the board, which means most of the joints will have failed. And the total test time to do this, though, was still 700 hours. So 2 PhD students did this, mainly Ryan and Derek supporting him. It's a lot of work. So here's some equipment I'll talk about tomorrow. That's an X-ray machine, that's the ultrasound machine. We've got this in my laboratory. And to do the scanning, total scan time in ultrasound about 242 hours. X-ray we didn't go into so much detail, 170 hours. Microsectioning to prove that we had the right images, another 160 hours. So it's hard work. Right, a bit of results. First of all, if you've got the solder bumps, you have to locate where they are. So Ryan himself came with this idea. We have team discussions every Friday, and obviously day to day we're meeting. So he did this Huff transform. He went up, got the software, wrote the program, and the Huff transform, in this case, is a circular Huff transform, looks for circles. So you can see these peaks are where he's identified where the solder bonds are. So then you put a red dot on to identify where they are from this processing. Then he segmented the image. And then finally, with the X-ray image, he worked out the percentage voiding. And the idea is going to fuse the two data sets together. Percentage voiding with the ultrasound. So here's the results. This is with ultrasound only. The one we're looking for is fractured, the red one. So normally the intensity is pretty flat. It's not completely flat, it's going along this sort of line. As the solder joint starts to crack, the red goes up, and when it's up here, it's totally cracked. So we're saying it's cracking, starting around about 24 cycles, and by about 48, 50, the joint's fully open. If you've got a good joint, healthy joint, it's going up and down, because see, it's not perfect, this is real measurements, but it's going along a flat trajectory. And this one of the voiding, it starts to go up, then all of a sudden, it doesn't really go up because of this bubble in there isn't reflected all the ultrasound back, whereas you would expect it to go up. So it looks halfway between a good and a bad joint. So when you look at the voiding, you can see on that joint, it's actually the voiding's shooting up when you got voiding, healthy is down there, and fractured is down there. So you can detect the void as well. So we plotted 109 results like this. So healthy joints are a plus on this side, this is a cluster. Fractured joints are over here, so mainly we're in two groups. So when you work out the grouping, we drew a line through the middle, but you still got this joint here, which is the one with the void. So this is healthy, a nice, donut, and this is a bright one when it's fractured. So you can see there, I don't know if you can read that, but you can see as it progresses from good to bad, as the cycles go up, it's moving across this barrier. Over here it's broken, over here and as these numbers are going up in this direction, in cycles, more cycles means more stress, so it's starting to break in this direction. So what he did next, this was Ryan's idea again, he classified it, so these are joints with voids, these are joints without voids. Then use the void information to see if you can identify that joint with a void that looked healthy but wasn't healthy. So there's the graphs. You can see this is an outlier here, giving you some cause for concern. And bump 100 has a failure beyond 96 cycles, so it's up there. Because we only ran the test for 96 cycles, some joints hadn't failed. So on the graphs, they're bottomed out at 96 cycles. They may fail at 104, 110. We don't know. We have to stop the test. So we've done all our, how do you display data? This is something you need to think about when you've got experience. How do you display your data? So we had a good discussion on this, and we came up with like a pseudo 3D effect. So this is a chip. Each of these bars is one of the solder joints, so it's 109 bars. The purple ones are the outer row of chips, and the turquoise ones are the inner row of chips. So how you expect it to fail is like this. You expect the corner joints to fail first, because at the corner the chips stress more and it goes up and down with its flexing. Then, because the chip's shorter in this direction and longer in this direction, it moves more in the longer direction. So expect the joints at the two ends to fail first, and you can see they're lower down the scale, so it did work. And in fact, the distribution across the sides, both the short and the long sides, should be a Gaussian idea, Gaussian shape. But because this is such a short size compared to these more or less all failed at the same time. You know, it's research, you find out new things. This one here, you can see, it's almost got a distribution type shape. This one here, because these joints haven't failed, would have probably continued on. So it's bottomed out on the top. So we did the experiment first. A lot of people do simulation first. And if you do simulation, it's always nice to verify your results with a practical example. So here's some simulation we did. You can see more or less the shape on the Gaussian and the ends is the same as ours. But the simulation is only as good as the data you put into it. So another thing we found out, we've been working on this a bit more because people don't consider it enough, is the floor plan layout. Not just on the chip, this is the floor plan layout of a PCB. Depending where the chip is on the PCB, look at these profiles, the shape of the failures is different. So the ones in the middle in this case, this one, is because the higher the peaks, it means the more cycles to fail, the more reliable. Ones in the middle are more reliable than ones at the edges. And this is for a freestanding board. So our latest test now, we've got 4 screws here. We put the boards in a fixture, screwed them down as it would be if you put it in a motor car. So that also adds to stress because the board is more constrained by the screws. We also on this board, some clever things we did. All these chips aren't just spaced randomly. Some of the chips are individual, such as this one. And others we've put back to back. So one on the top, one on the bottom, coincident. Because this is what a lot of engineers like to do if you're laying out a board, because it's easy to connect between them if one's on top of a board, one's underneath. But we found it fails quicker, so maybe not good idea. Then we placed some 50% that way, 50% that way, 50% that way, and so on. And we're just looking at the results now. But the placement of the chips on the board, position on the board, and what's on the other side of the board does make a difference for thermal cycling. We're also doing tests now for vibration, and we haven't got the results yet. So, conclusions. Acoustic and X-ray imaging can provide non-destructive testing of hidden solder bonds. Bear in mind, all these joints are hidden underneath a chip. This type is a flip chip. So there's no better way to do it in my mind. We can't monitor the lifetimes individually, because things like this voiding have to be detected by X-ray, but acoustic imaging can monitor most things. So when you put them together, we prove that this would work. Now just to conclude above that, 3D X-rays coming in. But do you know how much a 3D X-ray machine costs? I've used one at Manchester University, scanned some of our boards there to look at some solder joints, about £1 million. So you can only go to a specialist centre to do it. Everyone can't have one, maybe one in the country. But if you want to find a fault without destroying the sample, you can scan it. But do you know how long the scanning takes? These students had a lot of time scanning it, of chips, proper 3D, to scan it in a CT format and then reconstruct it. But the images are fantastic. And that's the future, I think 3D X-ray at the moment. Okay? Any questions? That's it then. So we'll have a break, and then I'm not sure the faculty members come. Sorry, faculty members coming at 12. Yes, please.
Behind all this discussion,
Yes.
we have a question that we think about nanotechnology. What are the basic key points to collect the knowledge about nanotechnology?
The key points.
Basic key points.
I'm not sure, to be honest. I'm not sure of the question. You have to discuss it offline. Okay, we'll finish there.